everyone. My name is Professor Rad, and this is Precalc video 2.1, an introduction to polynomials. In this video, we'll be talking about what a polynomial is and what different pieces of a polynomial are called. And we've got this huge definition that we're going to be going through and dissecting each of the pieces and the notation used. So I'm going to step out of the way so that in case you want to copy down this giant definition, you can do that. And then even if you don't understand what some of the symbols are, that's okay. Write them down, and then we'll go through in a moment and break down everything piece by piece. And then we'll do an example of relating these terms to an actual polynomial. So if you want to pause the video here and do that, feel free. All right, and let's go through this definition. So a polynomial function is going to have this form. Now, what this notation means, this pointy looking E thing, this is a capital sigma. So I'm going to write that off on the side so you know what to call these symbols. This is a capital sigma. If you've taken statistics, you've likely seen a lowercase sigma. This is just a Greek letter that we use, and we're using sigma like you would use S for sum. So this pointy looking E thing means the sum. And your summation notation is typically indexed. So we have here from I equals 0 up until n. So that means each of these i's, we're going to have a sub 0 x to the 0 power, and then we'll do plus a sub 1 x to the first, plus a 2 x squared, plus all the way up to some number n. So if you want to write this notation out longhand, you could do that. Let me shove this off to the side a little bit. So if I were to write this out, I'm going to start out with 0, and I'm going to have a sub 0 x to the 0. And then I'm going to add, because we have a sigma here for sum. Then we go to the next subscript, a1 x to the 1 plus, and you're just going to keep on going up until whatever n happens to be. If you are familiar with computer programming, you can think of this like a for loop. So for your index beginning at 0 and going up to a set value, you're going to create each of these items, and then you're going to be adding them together. So this is the shape that a polynomial has. You're going to be adding a bunch of things together that have some number times x to some power, basically. Then we have some restrictions on what those values and what those powers are allowed to be. So just a reminder that this funny looking E thing means is an element of, and this double R is real numbers. So what we're saying here with this notation is that each of these a sub i's is a real number. And we're going to call those values the coefficients. So when you have a polynomial, any numbers in front of the x's, those are your coefficients, and those numbers for this class are going to be real numbers. Here we have that an is not 0. What this means is that when you're doing your sum, n is the largest thing, right, that you're going to be adding up to. And we want this not to be 0. So we don't want to be adding further than we have to. That's basically what that's saying. And we're going to call that the leading coefficient. Then n is an element of the whole numbers. So this notation is saying that when we index our summation, we're going to be going up to some whole number. Now the whole numbers are 0, 1, 2, 3, 4, 5, 6, and so on. They're the non-negative integers. That largest piece, that's what we're going to call the degree. Then each of these components that's being added together is called a term. Oh, I didn't underline that one. Make sure we do that. So each of these contraptions is a term, and the term associated with the leading coefficient and the degree is called the leading term. And lastly, if you have a polynomial that's just one term long, that's going to be called a power function. So I know that this is very notationally heavy, and I know it's a lot of terminology. Get it? Terminology. So let's do some examples of putting these terms into practice. Okay, just a note real quick before we dig into the example. And this note is saying that a polynomial is in standard form when the terms are in descending order of degree. Now, the degree of a term in particular is just whatever its exponent is. So very often you'll be asked to write your answers in standard form. So that just means if you have like a cubed and a fifth term, the one that's got the fifth comes first, and then the cubed will come after. So we'll look at these polynomials and see if they're in standard form or not as we work through them, at least for the first one. So for this example, we're going to state the degree, the leading term, and the leading coefficient for each of these polynomials. And I ran out of space at the end of the board, so I just abbreviated with poly, but we know that means polynomial. So for this first example, I wanted to demonstrate with this one, this is not currently in standard form. That's because the squared term is written before the x to the fifth term. So if I wanted to rewrite that so that it would be in standard form, then I would have the negative 2x to the fifth first. Then I would have the 3x squared. And then I would have the 8. Notice that when I'm rearranging the terms, I'm using the operation that's in front of them also as the sign. So here we were subtracting 2x to the fifth. That means we have a term of negative 2x to the fifth. And 3x squared, we have our plus 3x squared because it was a positive. Now, I wanted to bring up standard form because, first of all, you'll often be asked to give your answers that way. But secondly, it also gives some light as to why the leading term and the leading coefficient are called that. When a polynomial is written in standard form, the leading term and the leading coefficient is the first term and the coefficient of the first term, because we've written that with the highest exponent. So in order to state each of these pieces for part A, the degree is our highest exponent. So in standard form, that's the first one. But you always want to check for the highest in case we do something a little confusing like that. So our degree here is the 5. The leading term is this whole first term, the negative 2x to the fifth. And then the leading coefficient is going to be the coefficient or the number in front of the x variable. So here we have negative 2 in front of the x to the fifth. So our leading coefficient is negative 2. Now, if you were wondering how this relates back to all those like a sub i's that we had in our definition, for this polynomial, a sub 5 would be that negative 2 because it's the coefficient associated with the term that has a degree of 5. There is no term with an exponent of 4 or 3. So a sub 4 is 0 and a sub 3 would be 0 because 0x to the fourth is 0 and 0x cubed would be 0. So that's how come we don't have any here. Then a2 is going to be 3. A1 is also 0 because we don't have any just x terms. And then A0 is 8. And you might be wondering, well, why doesn't this one have an x term to it? That's because if you have 8x to the 0, so long as x itself is non-zero, anything to the 0 power is going to give you 1. So this is really 8 times 1, which is why we get 8. So I'm personally, I'm never going to ask you to identify the a sub i's because I think that's just going too far down a rabbit hole, I think. But you will need to know the degree, the leading term, the leading coefficient, And also in a few videos from now, we'll also see that the constant term will be important. So the constant term and the leading term of your polynomial are going to be really important to identifying different features. So where did I throw my eraser? Here we go. So let's look at example B. So example B has -7t. So B is a polynomial with only one term. So this is a power function. You may also have heard this called a monomial before. So a monomial is a polynomial with one term. A binomial is a polynomial with two terms. And like in this case, we have a trinomial because it has three terms. And then we just don't give names for the ones that are bigger than that because that's being silly. So, I mean, there probably are names, but we're not going to refer to them. So for our power function, there's only one term. So we're going to get all the information we need from this single term. For the degree, when you have a value that has no exponent written on it, there's secretly an exponent of 1. So that means the degree of this term is a 1. The leading term is the only term we have. So that's going to be -7t. And the leading coefficient is the coefficient. So that's going to be the -7. All right, I'm going to take a moment and erase the board, and then we'll do part C, because that one requires a little more work. All right, so for part C, the very first thing that I notice when I look at this is that it looks different from a polynomial. It doesn't look like a bunch of terms being added together. So part C is a polynomial that's been given to us in factored form. And often a factored form of a polynomial is going to be really helpful because that's going to let us like solve equations. It's going to help us find x-intercepts, and it's usually a good form to have. But there are some disadvantages to having a polynomial in factored form, and that's that we can't pull out the degree immediately, and we can't pull out that leading term with its leading coefficient. And those are going to be important because they'll tell us certain information about a polynomial function. So if we have a polynomial that's been given to us in factored form, we can still find that information without having to multiply it all out, because this would be a pain to multiply out. So if I have 2x plus 1 and I'm cubing that, that means I have to do 2x plus 1 times 2x plus 1 times 2x plus 1. We can't distribute exponents. So then we're going to have these big polynomials that would be multiplying together, and it's going to get real long real quick. And we have relatively small exponents here. Sometimes you'll have exponents that are like 30, and you're like, oh gosh, I don't want to multiply 30 of these together. So there's a little cheat, because when you do multiplication of polynomials, so like, let's say I had that 2x plus 1, and I wanted to multiply that out 3 times. Well, if I first multiply these two out, the first thing I'm going to do is I'm going to multiply these two terms together, and that'll give me 4x squared when I do that. And that will be the term that has the highest degree when I do that multiplying out of these two polynomials. So I'm going to have 4x squared plus some nonsense that I'll be multiplying this 2x plus 1 by. Then when I multiply these two out, I'm going to have to multiply these two. And that is, again, going to be the highest degree term, because I'm multiplying the two terms that have the highest exponent. So 4x squared times 2x is going to give me 8x cubed plus some other nonsense. So when I multiply this piece out, the highest exponent I'm going to get is this cubed, and it's going to have an 8 in front of it. So what we can do to kind of cut out the work and not have to find all that nonsense is we can just pretend like these plus constants aren't here and see what we would get instead. So that's what I'm going to do. So for part C, when I look at this, I'm going to fudge it a little, and I'm going to think of this as -4 times just 2x cubed, and then times x cubed squared. And this is because, again, when I would go to multiply this all out, the highest exponent I'm going to get is going to come from multiplying this first term by itself however many times. Now we need our rules of exponents, so hopefully we remember those. When you have a product raised to a power, that's the same as taking each of these to that power and multiplying them. So you may think this is distribution, but it's not, because distribution is only multiplication of a number in front of something grouped by parentheses without exponent afterwards. So I like to think of this as an application property. So we're applying the exponent of 3 to the 2. And then we're applying the exponent of 3 to the x. And then for this next factor, we have x cubed being squared. So when you have a power to a power, you're going to multiply them. So 3 times 2 is 6. So then kind of simplifying this, we get a -4. 2 cubed is 8. X cubed, x to the 6. Now we can combine the similar factors. So 8 times -4 is a -32. And when I'm multiplying two expressions with the same base, I can then add the exponents. So 6 plus 3 is going to give me 9. So when I have this factored polynomial, the leading term is going to be this -32 x to the 9th. So we haven't gotten to degree yet. We just found the leading term though, so that's helpful. So -32 x to the 9th. That means our leading coefficient is the number in front of the x to the 9th. That's our -32. And the degree is the highest exponent, which comes from our leading term. So this is a degree 9 polynomial. All right, so that's going to conclude this first video introducing the terms of a polynomial and giving you some idea of what they can look like. For the most part, this factored form is going to be really helpful, although we will sometimes want to know pieces of it from a more standard form. So our mission throughout a lot of what we're going to be doing in these polynomial videos is building up techniques to factor polynomials. So how can I take a polynomial that's in this form and rewrite it so that it's in this form? So that way we can have like both forms, right? And it's always easier to multiply, even though this would be a pain, than it is to divide. So it's easier to multiply out or expand a polynomial than it's going to be to factor. So we have to find some tools and techniques to help us do that. So that's where we'll be heading in the next video. For now, we just wanted a quick introduction to these terms and ideas. So I hope you found it helpful, and I'll see you in the next one. Bye for now.